Early during my training to become a medical doctor, I spent much of my free time in the laboratory of experimental cardiology because I wanted to help develop new therapies for patients. And here I was confronted with the fact that most cardiovascular research is performed on animals or cells derived from animals. And I remember being very surprised to learn how much the properties of these animal hearts and cells differed from those of the patients that I saw in the clinic. I started wondering, how can we develop new effective therapies if these animal models are so poorly representative of humans? That's when I became fully focused on the problem and wanted to help find a solution. I decided to temporarily stop my medical training and fully spend my time in the lab to work on it. The big problem that prevents us from reducing animal use in heart research is shortage of human heart muscle cells. Unfortunately, adult human heart muscle cells cannot be multiplied outside the body. We can also not just take a piece of someone's heart, so we need to find another way to obtain human heart muscle cells. In the last few years, many researchers have been using stem cells to make heart muscle cells. However, this process is very expensive and laborsome, and the quality of these cells is suboptimal. We decided that we needed to have a different solution to easily and cheaply make huge numbers of high-quality human heart muscle cells. And to achieve this, we developed a new technique to multiply existing cells. Using virus particles, we equipped human heart muscle cells with a special tumor gene which can be switched on and off. When this gene is switched on, the heart muscle cells lose their specific properties and start to multiply. However, when we later turn this gene back off, the cells stop multiplying and start to behave again like regular human heart muscle cells. Using this new method, we can turn a single heart muscle cell into 1 quadrillion cells, which is the equivalent of 100,000 human adult hearts. When we tested the quality of these cells by, for instance, looking at their ability to generate tiny electrical currents, we found them to very closely resemble actual human heart muscle cells. And this is very exciting because it means that we have created a virtually infinite source of human heart muscle cells. However, we wanted to go the extra mile to prove that these multiplied human heart muscle cells are a better alternative than animal cells for studying human disease in the lab. And for that, we turned to the most common heart rhythm disorder, which is atrial fibrillation. 1 in 3 individuals will develop this irregular rhythm over the course of their lives. And this can result in symptoms like palpitations and fatigue, and increases the risk for developing heart failure and stroke. Unfortunately, current therapies are not effective in everyone, and newly developed therapies tested in animals frequently fail because of the differences between the animal and human heart. We took our multiplied human heart muscle cells and compared them to heart muscle cells from animals and stem cells. We found that only with our multiplied human heart muscle cells, we were able to accurately mimic atrial fibrillation in the lab, something previously not possible with cells from animals or stem cells. This new technology has already strongly reduced the number of animals used in our own lab, and we're actively working with researchers from around the world to make sure that they can and also will use our cells instead of cells from animals. At the same time, we're also helping researchers from other areas of medicine to apply our technology to cells from other organs, because this technology is not just limited to the heart. Taken together, this means that this new technology has the potential to have a big impact on reducing animal use across biomedical research, while at the same time resulting in better models and therapies for human disease. And that makes me very happy, because in the end it means that replacing animal models for human-based disease models is a win for everyone, for both animals and humans.